All right, today we want to talk about solubility product. It's from the upcoming chapter, but you're all a little bored with acid-base chemistry, right? And when we were in the equilibrium chapter, we went over what we call heterogeneous equilibria. And so the solubility product, KSP, it's an equilibrium, and we use it to describe things that we might say are slightly soluble or not real soluble, like magnesium hydroxide. You should have memorized solubility rules that state that most hydroxides are insoluble unless we hook them up with cations that render things soluble, like the alkali metals, sodium, potassium, lithium, or the ammonium cation. So we can have ammonium hydroxide, sodium hydroxide. Here is magnesium hydroxide. And we have a KSP value. So with all this in mind, we can write a word question. What is the pH of a solution that is saturated with magnesium hydroxide? We might imagine we have a beaker, the solids on the bottom, and there's some solution in there. So the first thing we need is a balanced chemical equation. Might look something like that. And then if we want, this is how you think about an ice table. We say we plop in some solid into this beaker. So at that instant, there's none of those ions. Some of this dissolves, some of this forms, some of this forms. So it's most convenient to call the species that has a coefficient of 1 X. So if I get X magnesiums, how many hydroxides form?
2x.
Absolutely. 2X. So if it's saturated, there's still solid in the bottom. Then we're going to have X and 2X. So what's the next thing we probably need? Got the balanced chemical equation, made the ice table, the equilibrium expression. So we say KSP is going to be equal to magnesium cation times the concentration of hydroxide. And then we need a 2 right there, right? Because of this 2 here. So now we get to plug in the last row of the ice table. And maybe I got a little sloppy here. There's solid there.
So that's why it's not included.
Absolutely, that's why it doesn't show up in the bottom here. So magnesium's going to be X. Hydroxide's going to be 2X. Alright, now we look at this and say, what's 2X squared?
4x squared.
4X squared times an X gives me?
4x squared times x.
Which equals?
KSP.
How about 4X cubed? Was what I was hunting for there. Alright, I did all my algebra all at once because you're all up to speed on these things. I divided both sides of the equation by 4, and then I took the cube root of each side. So now I can pull out my calculator, and now I'm going to plug in the KHP. 5.6 times 10 to the negative 12 divide 4 equals. Now we need to take the cube root of this. So make sure I didn't make any fat finger errors and see if you get the same answer. So now there's a few little twists to make sure we get the right answer in the end. We want to know pH. Do we know presently hydroxide ion concentration, hydronium ion concentration, or magnesium ion concentration? Yeah, magnesium. So that is X equals magnesium ion concentration. So 2X is going to equal our hydroxide. Things are going downhill. Now we have hydroxide ion concentration. So if I want pH, what should I do with my hydroxide concentration? Yeah, we're gonna use this concept or idea Yeah, so maybe the easiest way is to use the log version. So hopefully over the last week and next you'll see this more than once, a couple times. All right, so I'm gonna go POH, negative log of this number. Of course, I got the unrounded thing in my calculator. Log, answer. There's the POH. So of course now, I subtract that from 14. So there's my pH. And does that make sense? Yeah, that's a basic pH, and we're putting hydroxide into solution. Any questions over this type of problem? So from the equilibrium chapter, you should be able to deal with heterogeneous equilibria. And a lot of times it's lots simpler than the homogeneous. We didn't get a quadratic. We got something we could just use algebra to solve for x. We had to realize x equaled magnesium ion concentration. So we had to multiply that by 2 to get hydroxide ion concentration. Once we had hydroxide ion concentration, we use Kw because we're in water. Kw is in control. If we know hydroxide, we know hydronium, and we decide to work with the log version of the equation. Found POH. There's our POH. Don't select a pH of 3.65 on the multiple choice question, which students do a lot. That's POH. pKw minus POH equals pH. Any questions on this problem? Polyprotic acids. That means more than one proton can come off of it. So we have diprotic, triprotic. It says here if the difference between the Ka for the first dissociation and subsequent dissociation is 1,000 or more, we can treat it like a monoprotic acid and ignore the second one. That's what this says here. If the difference between Ka for the first dissociation and the subsequent Ka value is 10 to the third or more, the pH generally depends only on the first one. So ascorbic acid, has anybody ever heard of that before? Ascorbic?
Isn't that like in limes and stuff?
In what?
Like limes.
Limes? Yeah. Stops you from getting scurvy. We have a different name for it.
Vitamin C.
Yes, vitamin C. Very good. So looking at this, I think the difference is like 10 to the 7th, right? Let's think about our exponents. So that means if I dissolve some vitamin C, ascorbic acid, the pH is probably determined a whole lot just by this first Ka, and I can ignore these second ones. Let me see if we can find one. What about tartaric acid? I think tartaric acid might be an equilibrium problem beyond the scope of this course, because the difference here is only, I'm getting 10 to the second difference, not 10 to the third.
So basically, you subtract them from each other. So
Yeah.
oxalic acid.
Actually, I'm dividing, and then I'm using the property of exponents. When you divide exponents, you can take their difference or sum them when you multiply. Yeah. So that's how I'm looking at this and saying this is a difference of not 1,000 but 100. All right. Here's ammonia. If you learn one thing, you're going to learn that ammonia is NH3 and it's a weak base. And we put it in water. Water acts as an acid, gives ammonia a proton, and that forms hydroxide. And then we can look at these things and label what was left over from the acid is a conjugate base. What's left over of the base is called a conjugate acid. And conjugate acid-base pairs differ only by one proton. Well, from a structure, how do we identify a weak base? Typically, if it's a neutral substance like ammonia, we see if you do the Lewis structure as a lone pair of electrons. Then if you look at water, you see two pairs of lone pair of electrons, and we've seen examples where water acts as a base. It's amphoteric. Of course, it acts as an acid when it's around ammonia. And so here's our products in water. We get the protonated base and hydroxide, and it says anions of weak acid are bases, and that's what's depicted here. Like if I had sodium fluoride, fluoride has that negative charge. So I'm going to come back here real quick and say here's a base, and here it's conjugate acid. Now in the lab, you've done some experiments with ammonium chloride. It dissolves up and it's endothermic and gets cold, and it's also a fertilizer, so we can dispose of it easily. So here's ammonia doing its normal base thing. Now if I took some ammonium chloride and dumped it into a beaker of water, it would do this thing. And so here we can see clearly that ammonium chloride behaves as a weak acid. And so I can write a Ka expression. I have my hydronium ion, ammonia up top. Down below I have ammonium cation. Just imagine there's the little aqueous symbols everywhere. And here for the Kb, this is the new thing we just saw today. Ammonia's down here. Water didn't show up because we'd have the little subscripted L for liquid. So our products are up top and these are down below. So if I write the Ka expression for this one, Kb expression, and the Ka for the next one. Alright, this is turning into lots of work. How do you feel about manipulating equilibrium constants? Alright, we've done it before. Like if I was going to add these equations, what would I do to the equilibrium constants? What?
Multiply.
Yeah, we multiply them. And since we have this expression here, the whole reason, and I could have just read it off the PowerPoint slide, but that may not have the effect that I'm hoping this does. Alright, so can I do any simplification?
Yeah, you can cancel by chance.
So that cancels there. This cancels here. What am I left with?
Hydro times hydrogen.
Absolutely. And that equals Kw. And so what that means here is if I add these up, I'm going to go Ka times Kb equals Kw. So hopefully, I could just tell you this.
So is that applicable to all of them?
Any weak acid and its conjugate base. For any weak acid and its conjugate base. And then we get to my favorite word, logify this equation if we need to, and go pKa plus pKb equals pKw. Alright, so in the minute that's left, I'm going to pull out my calculator and let's look at this thing. If I multiply these two numbers together, what am I going to get? Here we go, 6.8. How about negative 14th? Where was I at? Here we go. 6.8 times 10 to the negative 4th times 1.5 times 10 to the negative 11th. Yeah, my calculator says 1.02 times 10 to the negative 14th. And so these rounded a little bit. I can live with this. I don't know if I can live with writing with mouse. Alright, this is a nice ending. Next time we meet, we're going to talk about acid-base properties of salts. And when an acid reacts with a base, what are the products? A salt and a water. You'll get more of that today. I'll see you